Hello everyone, I'm going to do an example solving a trig equation where we're going to need to use one of the power reducing identities to help us solve it. So my equation here, the sine squared of x plus the cosine of 2x minus the cosine of x is equal to 0. As we've talked about before, when we're trying to solve a trig equation, we want to end up with a single trig function, and that is equal to some value, whatever that value happens to be. And then from there we can use our inverse idea, or we can use the unit circle to find out what angle measure would give us that value. Looking at this equation, I see a sine squared of x. My first instinct would be, well, maybe I can factor this. However, we don't have any other signs anywhere in here. We have a mix of sines, we have a mix of cosines. So I want to do a little bit of rewriting. So this is a good candidate to use our identities. So the first thing, the sine squared of x here, if I can reduce the power of this, just with that identity, I know that that's going to be the same as something with cosine in it. And then I'm going to end up in the equation that has all cosines. So let's try that out first. So the sine squared of x, our identity, that is the same as 1 minus the cosine of 2x all over 2. And then I'll rewrite the rest of this. Okay, so now we have an equation that has all cosines in it, and we should be able to hopefully work with this a little bit easier now. So we do have a fraction over 2. I have a cosine of 2x here, and there's a cosine of 2x there, so I want to be able to combine those like terms together. So to make this the easiest, I think I'm just going to multiply everything by 2. That will take care of that denominator, and the right-hand side, multiplying by 2, it's just going to stay 0. So 1 minus cosine of 2x plus 2 cosine of 2x, and then minus 2 cosine. Now we can combine these like terms together. So minus 1 plus 2. So here we have 1 plus the cosine of 2x minus 2 cosine of x is equal to 0. Great. So this is all in cosine still. However, the cosine of 2x and the cosine of 1x don't necessarily work together too nice. They're not like terms, you can't combine them together. But we do have an identity that we can work with the cosine of 2x. We've talked about this before, but the cosine of 2x, there is actually 3 possibilities for this one. One has cosine and sine, one just has sine in it. The one I want to use in this case is the identity that only has cosines in it, because my equation only has cosines. So the identity that only has cosines in it, so substituting that out, is 2 times the cosine squared of x minus 1. So we took the cosine of 2x and we substituted that with this identity right here. And hopefully you can see that that is going to help us out quite a bit. 1 minus 1, okay, so that's going to give us 0. Taking a look at what we're left with, they both have a common factor of 2, so we can divide that out. So I'm just dividing both sides by 2. So the cosine squared of x minus the cosine of x is equal to 0. Okay, it's good. It's still equal to 0 because now I have cosine squared, cosine to the first. I can factor this, and I can use my 0 product property. So factoring that out, we get cosine times cosine of x minus 1. And then our zero product property, we can separate that into two equations. So our two possibilities, when is cosine equal to 0, and when is cosine equal to 1. And now we can kind of use our inverse idea. We can take a look at the unit circle to figure out where this happens. So let's see. When is cosine equal to 0? So taking a look at the unit circle, cosine is 0 at pi over 2 and 3 pi over 2. Okay, cosine is the x value, so when on the unit circle, when is x equal to 0? And then when is x equal to 1? We have either 0, or you can think of it as 2 pi. All right. Now our equation, it did just say solve, so why don't we list off all possibilities. So x is equal to pi over 2, and then plus 2 pi n. The period for cosine is 2 pi, so every multiple of 2 pi will end up with an answer. We have 3 pi over 2 plus multiples of 2 pi. And then from this one, we also have just multiples of 2 pi. So then let's say where n is an element of the integers.